All right, guys, so we're going to start with our lesson on 6.1. Let me get back to the very beginning, sorry, which is on centripetal force and acceleration. So um, centripetal force, centripetal acceleration, and the law of universal gravity. So we've already discussed acceleration at length, and acceleration is the rate of change of velocity. Things speed up, slow down, or turn as a result of different types of acceleration. We have covered speeding up and slowing down. We also looked at this with other forces. So like if we wanted something to speed up, so if I had my object here and it was at rest, and I applied some force or it was moving to the right here. So this green box is sliding to the right, and I wanted it to go faster. We would apply a force to it. So we would apply a force that would go in the same direction if we wanted it to speed up. So our purple arrow there, which represents a force, and this black arrow represents the velocity. I'll just label those real quick. So if the velocity was that way, and I applied a force to it here, that would cause it to speed up. So because they're in agreement, it would speed up. If I wanted it to slow down, we've talked about what I would do here. So I would just flip this arrow over and make it go the other way. So if I somehow applied a force going the opposite direction to the way that it's moving, then the object would slow down. So those are two types of motions that we've studied in kind of straight line motion. We can also have things turn. So if you want something to turn, you're not going to kind of push it in the same direction or in the opposite direction, like in the first two cases we just talked about. What we'll do, we're going to try to rotate it. So if I take this object, and that's not going to let me do it, let me just try another arrow. So if I draw an arrow kind of going down that way, and that is the force. If I move this force here, that didn't all work, but let's move the pieces. There we go. If we have this force kind of pushing it in a direction that it is not in the same direction it's moving or the opposite direction it's moving, it would cause it to turn. And these types of accelerations are called centripetal acceleration. So an centripetal acceleration, or centripetal, the word centripetal means center seeking. It always points towards the center of the circle and keeps an object moving in circular motion. So if something's going in a circle, there has to be something pushing inward towards the center of that circle to keep it moving in that circle. Otherwise, it would not maintain the circle. So this type of acceleration is at right angles to the velocity. So right angles means perpendicular, like we drew in this picture back here. So this is basically a right angle. So the velocity is going one way and the force could be perpendicular to it. Because of this, it would cause this object to kind of turn that way. That would make sense. That so if we had this velocity going to the right and this force pushing down, it would turn like that. So this type of acceleration is not going to speed it up or slow it down. It just causes it to turn. So it's the third type of effect of acceleration that we could talk about. Oops, skipped one. So to calculate the centripetal acceleration is AC. That's that variable there. It's v squared over r. So v squared, v is the tangential speed. Tangent in this means touching the circle at one point. So the velocity that's going in the straight line, and that's measured in meters per second. And then you square that because it's v squared, and then you divide it by r, which is the radius of the circle that it's traveling in. And that would be the centripetal acceleration that is acting on it to maintain that circular motion. We've already talked about if there's an acceleration, there's a force. So there's a special type of group of forces called centripetal forces, which cause things to turn again. So it's any force or force that is responsible for a centripetal acceleration. Centripetal force is simply just the mass times the acceleration again. So it's Newton's second law, F equals ma. It's just got these little subscripts of c. So Fc equals m. AC, you could replace AC with the equation for centripetal acceleration we've covered before. It's v squared over r. And again, the idea of centripetal, that word means always towards the center. So it is not away from the center, it is towards the center. And what people get confused about, one of the things that people get confused about in this part is they think a centripetal force is a new force. It is not. It is just a force that is directed towards the center. So all the forces that we have covered already, the gravity force, normal force, friction force, tension, any other applied force like somebody pushing or pulling, those can all be centripetal forces. So it's more of like a net force idea. It's the net force going towards the center is the centripetal force. So that's what I was getting into. So anything or any combination of forces, so it could be more than one force pointing towards the center, and that would be centripetal. If you have a force pointing away from the center, that is not centripetal, but we consider it when we're trying to figure out the net centripetal force. But if something's moving in a circle, there has to be something, the sum of all the forces that are acting either towards the center or away from the center has to point towards the center, or it wouldn't maintain that motion. Okay, so here we're just going to go through some examples to kind of talk through the idea. So if you imagine this person here is swinging a mass by a string, and it's going in like a horizontal circle, so like sort of like a lasso or something like that. You might imagine doing this at some point. So the weight's tied to a string and spun in a horizontal circle. What's the identity of the centripetal force? So we're not calculating the centripetal force in this situation. We're just trying to say, what is creating that centripetal force? What is the force or the specific force that is keeping it in the center or going to the center? So if we look at the forces that are acting here, there's gravity pointing down. Is that a centripetal force? So is Fg here, or depending on the letters that you're using, I sometimes write Fg. That's the same as big G if you want to write it as that. That is not going to be the centripetal force. They are not centripetal because they're not pointing towards the center. So really, we just have to look at and worry about the things that are pointing towards the center. The only thing pointing towards the center is that string. So the centripetal force, Fc, is equal to the tension. That's the only thing that's there. So that's the tension. So that could be T or Ft, depending on how you write it out. Either way is fine. And then you could set that equal to MAC and solve for whatever you need to if you're given the numbers. Another one here is we're going to identify the centripetal forces acting when you're in a like a looped roller coaster. So if you imagine this roller coaster is going around the loop, and we want to think about the forces acting, and we want to decide what is the centripetal force. So I don't know what that square is there for. Oh, but here is like, if this is like a picture that box is supposed to represent like maybe one of the cars when it gets to the top. This is the circular path that it's following. If we identify the forces here acting, I would say there's definitely a force going down. That's the force of gravity. So we can draw that in. So if I draw in the force of gravity here, I'll use green for gravity. So we got some force of gravity pointing down. I'll type that in as Fg or Fg or G, whatever you prefer. It doesn't really matter, the labels, as long as you have it labeled and I understand what you're talking about. So that's there. Is there anything else that could be pushing or pulling towards the center? I would say there's friction is going to go the opposite way to this motion. There's no tension. There is a normal force though. So if you imagine the track, and this is a sort of a weird situation, the track is pushing on the car, and it's going to push in the same direction as gravity in this case, which is not the norm for the normal force, but it is kind of what's going on. So if I draw an arrow going down here for that, and I can label that Fn or N, depending on, again, the subscripts that you're using, or the labeling that you're using in process, it doesn't matter which. But we have both of those. At some point, like the faster it goes, the faster this roller coaster is going around the circle, the more the track has to push in. So this normal force is the track pushing inward, and that would increase with a increased speed, because there'd be a bigger velocity, which causes a bigger centripetal acceleration needed, and that would require a bigger overall force. You're not going to have to really do a lot with this. I'm just trying to show you that the centripetal force is caused by something else. Okay, so let's go ahead and practice a couple of problems here in a second after we get through the next concept. So we're going to go back to this concept of gravity. So when we've calculated gravity and we've looked at gravity so far, we've talked about it as the weight of an object. And we'd use this equation Fg or big G, depending on, again, which letters I use. It doesn't really matter. But big G or Fg is equal to mg. So that only works near, that's the equation only works near the surface of the Earth. And things can have weight or gravity when they're not at the Earth. So like if there's some other planet, they need another equation, or if you had a different situation where it is not right at the surface of the Earth, but maybe you have something that's like orbiting the Earth, and we don't know, okay, what is the force of gravity acting in it on that point? And in order to calculate those things, we're going to use a more general statement for gravity. This one's only specific for the surface of the Earth. We're going to use a more general one, which is called Newton's law of universal gravitation. So Newton's law of universal gravitation is created by Sir Isaac Newton, again, one of the smart guys that came up with a lot of these ideas. And he described it as the attraction of two masses. So it doesn't have to be the Earth and something all the time. It could be any two masses. So you are attracted to anything else that has mass. The reason why we don't really worry about this equation very much is that attraction is really, really small most of the time. The only time that attraction or force of gravity kind of gets to things to levels that we notice it is when you have at least one really massive object in the situation, like the Earth. So, so in this case, this is like the generic picture for it. So this circle here represents mass 1, this circle represents mass 2, and there is a force of attraction that is trying to pull them together, and that is the force of gravity. So the equation for it is Fg for force of gravity is equal to big G m1 m2 over r squared. So Fg, again, force of gravity, force due to gravity, that's the universal equation for it. Big G is something called the universal gravitational constant. So that value, you're just going to put in 6.67 times 10 to the negative 11. Don't worry about the units so much. It works out to be newtons. So these are just to make it so that the equation works and gives you newtons at the end. But this is a constant value. So you're always going to put that number in, and is universally constant, so it's good everywhere. M1 and M2, those are the masses that are attracting each other. So M1, M2, they're both maybe different sizes. It doesn't matter. So this could be like a planet, and this might be the moon. And we want to figure out what's the force of gravity between those two things. Finally, the last thing here is R. And just make note, R is squared. So you're going to have to square that in the equation in the math, but R is the distance between the centers of masses of the two objects. If these are normal sized objects, it's basically the distance between them. But if these are big objects like the Earth or the sun, and you have to worry about that distance is significant. And then you have the distance between those two masses. Okay, so that is the equation. We're going to work through an example, and we're going to tie it back into centripetal ideas in a second here. Right. So let's try this problem. So this problem reads, try to make it a little bigger. See if that helps. You're supposed to use the universal law of gravity to determine the force of gravity between the Earth and a 70-kilogram physics student if the student is standing at sea level, which is a distance of 6.4 times 10 to the 6 from the Earth's center. And then we're going to calculate the weight of the student the normal way that we would do, and show you that this equation works for everything. So it doesn't have to be a weird situation. It can be our normal situation. It's just more, I would say, involved. So we just use the shortcut, and maybe I'll do part B first because that seems easy. So so for part B, that started, we would do Fg equals mg. That's the weight of the student standing on the Earth. And this is what you would do normally for this problem, but we're going to work it out with the other one. And the student is 70 kilograms, and they're standing, and their acceleration due to gravity on the Earth, if they're at the surface of the Earth, is 9.8. You could also use 10. So it's going to be around 700. I'm going to jump to Desmos here and just type in 70 times 9.8. So I get that number, and that's 686. So coming back here, this answer is the student weighs 686 newtons. We would expect that's going to be our answer using the other equation. So that's sort of what our answer should be, because it should give us the same thing. So let's look at the equation here again. So Fg equals big G m1 m2 over r squared. I've already typed in some of this stuff to make it go a little quicker. So I'm going to plug in the universal constant. I'm going to plug in the masses that are involved. And then I'm going to plug in the separation between those two masses and square it. So looking through the 6.67 times 10 to the negative 11th, that is the universal constant. So that's why that's there. 6 times 10 to the 24th, that is the mass of the Earth. 70 is our student. And then 6.4 times 10 to the 6, that is essentially the radius, the average radius of the Earth. And that is going to be squared. So I didn't put this in the calculator because I wanted to show you how it works on the calculator, what it looks like. So we're going to do that now. So we got 6.67 times 10 to the 11th. Let's see if I can find it. Trying to make this and it's the negative 11. Sorry, I spoke. Okay. And then we're going to take that and multiply it times the mass of the Earth, and our mass of the Earth, we said, was 6 times 10 to the 24th. Then we're going to multiply that by 70 because that was the mass of the student. All right. And that's the numerator. So I'm just going to leave that. So that would go on top of the fraction. And then I'm going to take that answer, which I want, and divide it. What's going on here? There you go. And divide it by this whole thing. There we go. It'll be smart and put that in. I'm going to divide it by the radius of the Earth, which is the 6.4 times 10 to the 6. So 6.4 e to the 6th. Ooh, wrong e. Times 10 to the 6th. And then I need to square that. All right, so I think I have everything. It looks good. And we got a number like 684, so 683.935. If we look at that compared to our answer for the other one, so I'm gonna just try to copy that. Hey, Mom.
Hi, Bill. I see I missed your calls. I'm sorry.
Yeah, were you out or about, or what's going on?
But I had my phone turned off.
Oh, okay. I figured as much. I called the house, nobody answered, so I figured you were just out running around.
Yeah, Dad's sleeping.
Oh, okay.
He didn't get very much sleep last night, so I've got to get him up at noon and feed him and make sure that he's up. So, what's new?
Oh, nothing. Just seeing what was going on, how you guys were doing. We got we cooked the corn and cut open the melons and ate a tomato or two. Everything was good.
Yeah. Their stuff is good. I mean, his stuff is good. The watermelon has seeds in it, but it's very good.
Oh, okay. Yeah. Ours is fine.
Good.
And then let me see. Oh, Lee used the 30-cent
Good.
thing over at the gas, so
Good.
figured I'd tell you that so you knew it was used up.
Right. I mean, it's silly to have it go to waste. And get 30 cents off on it. And you don't have to go all the way out to Sam's. Sam's went up again today.
Oh, did it?
So, yeah. So she probably did better at Safeway.
Yeah, she said she had like a half a tank or something to use, so or fill up. So I'm not sure how much she put in, but she used it, she said, so that's good.
So it's not too bad out there.
No, it's supposed to be kind of nice today. It's not awful.
Yeah, I had to run out and get Daddy some of the inserts at Friday. And so that's what I was doing. And I accidentally turned my phone off.
Well, I figured you were just running around doing whatever.
No, it was too late to get him
Breakfast.
Well, he wanted biscuits and gravy, but it was too late. So I'm going to fix some eggs this morning.
Oh, okay. Well, it's almost noon. It's more like lunch, but that's okay.
Well, it's good for him to eat because the eggs are good for him. So.
Oh yeah, I wasn't saying he shouldn't eat it. I was just saying he should. He needs to get up, and get moving.
Well, he was really tired this morning when I got up, and he was out of it. I mean, totally out of it. So, And the game yesterday, what was the final score? I watched into the second half and it was still 1-0.
I think it ended up 3-0.
Oh, did it?
Yeah.
Of course.
Barcelona won.
Oh, okay. All right. So that was about it.
Okay.
Thing is on today. So.
Yeah, I think the soccer games are already gone for today.
Oh, okay.
But I made some eggplant last night. I was gonna bring it over.
Need any. I still have the one from the last time that you.
Okay. All right. I will keep it then.
Yeah, freeze it there because I still have that frozen here. I haven't made spaghetti sauce recently, so I'll do that later on this week. I have too much in
the freezer.
Yeah, right now I have 2 of the chicken enchiladas and the meatloaf and pepper and it's mostly filled. Put it that way.
Well, that's good. Hopefully you don't have to make too much.
Yeah, and so Monday I have physical therapy. Tuesday we have Dr. Patel and haircuts, and then I thought maybe we could go down Wednesday or Thursday to get that car done.
Okay.
If you can do it, if you can't, that's okay.
Yeah, I gotta figure out what my schedule is. I think I have a doctor's appointment with Scott on Tuesday, I believe. What time is your appointment on?
Mine's 11:15.
Okay, I think I'm about the same time. All right. So you said your appointment with Dr. Patel's when?
11:15.
Okay. Well, I might be able to come to that. I gotta take Abby's going to visit a friend who just moved in Charlotte, so we're putting her on a flight later this week on Wednesday or Thursday. I can't remember which. One of those 2 days. But yeah, Mom, I'll be able to go get the car and bring it up. It's not a problem. You guys don't have to go.
Well, I don't want you to leave your car down there, Bill. So we'll drive down with you and we'll check the house out, and then you can take the car up. Just bring it on up.
Well, either you're gonna have to drive it up, or you'll have to drive my car up then.
I'll take my car down.
Okay, well, we'll figure it out.
Okay. Okay.
It might not be Wednesday. I forget. Let me check. I'll double check good day.
Okay, that's all right.
And let you know. But yeah, towards the end of the week, we should be able to do it, I think.
Okay. So she's going. Oh, that's nice. She's going to Charlotte.
Yeah, for a couple days. I think till the next week or so. Spend about a week down there, and then she starts up preseason the week after that. So.
Where's them?
I'm not sure. They just moved there like a month or 2 ago, so I'm not exactly sure what town it is, but it's around in Charlotte.
Oh, there's a lot of little towns.
Yeah, I know.
Yeah. Well, that's nice. I'm glad she gets to go down to see her.
Yeah.
Okay, well, you take care.
All right. Well, yeah, I'm just doing some work. Hopefully get that done and then be good.
Okay.
All right, Mom. I'll talk to you later. Bye. So all I did was copy the calculator printout. So here it is. So again, we got 684 using Newton's law of universal gravity, which is a little more precise. And this 70 times 9.8 is 686. We're talking about 3 newtons, which is not a lot of force. So it's not something you have to worry about too much. So it's good. It works. The only other thing I want to mention, again, make sure you square the bottom here, because that's a really big common mistake that people make. And then be careful making sure you get these numbers in with the times 10 to the on your calculator. If you have any difficulty with that, just reach out to me and I can generally talk people through it and make sure they're good for that. So these numbers are essentially the same number, the 683. And really what happens, the 70 is this 70. all these other numbers put together, so this is like the universal constant, the mass of the Earth, the radius of the Earth, those aren't changing. They're constant. So if something's close to the surface of the Earth, those numbers are going to stay the same. And when you put that in your calculator, you get the 9.8 or around 9.8. So that's where that 9.8 number value comes from. So now you know it's not just some random thing they made up. Like it's from this equation. All right. So we got a couple more examples, and then I'm going to talk through the simulation that you're going to be working on. So for example 2, it says find the force of gravity acting on a 1,000 kilogram satellite that is in circular orbit around the Earth. Again, the mass of the Earth. Sometimes I use this notation E, this capital E. Make sure you don't use lowercase e on your calculator. They are different for things. This E just stands for times 10 to the, it's like a shorthand. So it's an abbreviation. So 6 times 10 to the 24th at a distance. And then this satellite is further away. So it's like a satellite, like, a television satellite or a radio satellite. So it's 1.68 times 10 to the 7th away. So it is not at the radius of the Earth. It's more than that away. So this is the total distance away. And we're going to find what is the centripetal acceleration acting on the satellite, what's the direction of the acceleration, and then at what speed is the satellite orbiting the Earth. So there's a couple different things. This is where we tie it back into centripetal stuff because it naturally fits. Okay. So again, just starting with the gravity equation, I plugged in the numbers here. So it's 6.67 times 10 to the negative 11th. That's the constant. 6 times 10 to the 24th. That's the Earth. 1,000 is now the mass of the second object or the satellite. And then this is my new distance. So let me go back to the calculator here. And I'm going to put in 1,000. Oh, it didn't work. Just copy that and see if it'll take it. Yeah. All right, so I might have to type it in again. So 6.67 times 10 times 10 to the negative 11th times 6 times 10 to the 24th times 1,000. All right, so it did work. It was 4.002 times 10 to the 17th. And then I'm going to divide that answer. And divide it by the distance, and that distance was 1.28 times 10 to the 7th. And then we need to square that. So there we go. So this is the answer that you should get, hopefully. Yeah. So 2,442.63 or so. So 2443 is fine. You don't have to be that exact here. 2443, we'll just say that's newtons. And then we can keep it moving. So that's the force of gravity acting on the satellite at that point. And it says, what is the centripetal acceleration? So to get the centripetal acceleration, we want to use that equation. So centripetal, we don't know the velocity, we don't know. So we can't use that yet. We're going to use that in part D. We're going to use the centripetal force equation where the centripetal force is equal to mass times acceleration. So we know the force, we just got that, is centripetal force is the force of gravity, which is 2,443. And so that's going to go in here. We're going to solve this for AC. I did that already. So we want the centripetal acceleration. So it'd be FC divided by M. So 2,443. And then we're going to divide it by the mass, which is 1,000. Let's talk about why I use the mass of 1,000 and not the mass of the Earth. The centripetal acceleration is the thing that is moving in the circle. So the Earth is the thing that's in the center, and the satellite is orbiting around it. So the satellite is traveling in the circle. So that's why divided by 1,000. So that's going to be something like 2.443. Bigger. We're good with that. And the unit for acceleration is still the same unit, which is meters per second squared. There we go. Part CS, which direction is the acceleration acting? This is a centripetal acceleration or a centripetal force. So remember all those things, whether they're accelerations or forces, they always act towards the center. So all centripetal accelerations and forces are inward towards the center of the circle. The last part of this one says at what speed is the satellite traveling? So we're going to solve for V. We're going to solve for the velocity. And this is the equation for centripetal acceleration. So it's V squared over R. So this is our acceleration. And we basically just have to plug in the numbers. So if I solve for V squared, I'm going to take the R to the other side. So it's R times AC. And then I'm going to plug that in. R was the 1.28 times 10 to the 7th. We're going to multiply that by 2.443. And then that's V squared. In order to get rid of the squared, you got to do a square root. It's not that one. There we go. You got to do a square root. So on your button or your calculator, that's the button we're looking for. So let me jump to Desmos. I'm going to multiply that by 2.443 because that was our acceleration. So just going back, yep, 2.443. So that's that number. And then we need to take a square root of that. So we'll hit enter and then we'll take a square root of the answer. And we get 5,592-ish. So that is how fast it is moving. So it is moving pretty fast. 5,000 meters per second is a lot. But if you imagine 5,592, if you imagine a satellite, in order for a satellite to move and to maintain its path, it's going to be going really fast. Like the Earth travels at like 10,000 miles per hour or something crazy like that. So this satellite is going fast around the Earth. That's okay. So these numbers for V might be larger than expected. Don't want that. So the last thing I'm going to do to close out this video is just talk about the simulation that you're going to be doing. So it's the universal gravity simulation is the name of it. And essentially what you're doing is you're investigating how changing either the mass or the distance in a situation that involves two masses will affect the force of gravity. So it says set up the mass of each object, whatever you wish, do not change it. Use the ruler, vary the separation between the masses and record how these forces change. It says do 10 unique separations, record info on a table. So you're going to look at the simulation, which I'm going to show you. The only thing that's a little weird is micronewtons, so don't worry about it too much. As long as you get a consistent constant, it's okay. So I'm going to jump to the Universal Gravity Lab. There it is. So you're going to go to this. The link is on D2L. You're going to click begin. It's a Doctor Who person, I guess, who made this. And what you need to do is you need to look at the object. So for object 1, that's fine. You just write down that number, 406 or 7. It's not going to be the same. It changes every time. For the other object, it's a bigger number, 1.47 times 10 to the third. And then for the ruler, you're measuring from the distance from the center to the center. So this one's really close to 6, a little bit more than 6. And what you're going to do is you're going to click on force. So it says 1.1 micronewtons. That's fine. So this is the micro symbol. Make sure it has a U. If it changes to an M, you want to stop on that part and try a different one, but you want to make sure it stays U all the time. To get it back, you just click. So I would type in my values here for this. I would type in the separation is like 6 meters. I would write in these two masses, and then I would write in the 1.1 here. And what we're going to do is we're going to vary the mass. So, or I'm sorry, vary the separation. So I'm just going to take object 2 and start moving it closer to object 1. So I hit it 2 spots, and it's like at 5.6 there. And then I'm going to hit force again. I'm not changing the masses in this part. So I'm going to go to force. Now it's 1.2. So it went up a little bit as it got closer. If I move it in another 2, and I look at the force, now it's up to 1.4. If I move it in another 2, I'm a little under 5, maybe 4.8. If I look at my force, I'm now at 1.7. So you're just going to do that and keep moving these things either closer or further away. It doesn't really matter. If you move them further away, it might get too small. But you're going to keep doing this and record 10 different data points. And then once you get those data points, you're going to graph it. So going back to here, it says use the graphing tool on the utility. And then you're going to take a screenshot of that graph and you're going to show me a sketch of it here. So you're going to just draw a sketch on your thing, whatever's happening, and you're going to write a description. And you're gonna say what's going on. So with the descriptions, just as the separation increases or decreases, what happens to the force, depending on how you moved it. Okay. For the second and third parts, they're really similar. You're gonna keep mass 2 the same and the separation the same, so you're gonna get at some distance. And so I could just start back here, say that's the distance I want to maybe move it to a whole number. All right, so it's pretty close to 3. I know my mass 2 is that number. Mass 1, that's the thing I'm going to change. So where it says bigger or smaller, I'm going to change it. But right now it's 4.2 for the force. And what I'm going to do is I'm going to start maybe increasing the mass. I think that's the better way to go. So I'm going to take object 1 and I'm going to make it get bigger. So now it's 720. And I go to the force, it is now 7.5. And if I go to mass 1 here and make it bigger again, so now it's like 1,160 kilograms or 1.16 times 10 to the third. Now it's 12.1. So you're gonna do that, and you're gonna see a relationship between changing mass 1 and the object and the force on the object. Again, you're gonna graph it. You're gonna get a description, and then for part 2 or part 3, excuse me, you're changing mass 2. So you're going to set mass 1 to be whatever the number is, the separation to whatever the separation is, and then this will be mass 2, and you're going to see the relationship there. So that is what you're trying to do, and I will stop the video there. Hopefully you're caught on and you'll understand it. If you have questions, though, just message me. Talk to you guys later. Be well.